Presentation number 4 in this session is from Ozan Celik. He's with Structural Health Monitoring. He's a group leader with Geocomp. He's going to be presenting on dynamic assessment of the Fred Hartman cable stay bridge using OMA. This is an interesting one for me because this is one of our bridge. I am hearing the results at the same time you are, so I'm hoping for an interesting study with some uninteresting conclusions. But let's welcome Ozan, please.
Thank you so much. I hope I'm going to do a good job today. Before I begin my presentation, I would like to take a few moments and thank you everybody for being here and being a part of this incredible meeting. I remember for my first time, I believe it was in either 2019 or 2020 in North Dakota, first time attending one of these meetings. And since then, I mean, it has been a great pleasure for me to share my experience and learning from others, and also, you know, Darlene, Nancy, Todd, all of the other people that I probably are kind of missing out pronouncing their name. Thank you so much for everything. So today, the presentation is going to be about a rather maybe strange concept for some of you. When we say OMA, what we mean by that is operational model analysis. This concept has been out in the research fields for more than probably 30 years. However, the integration of that idea to real structural engineering or bridge engineering is now taking traction. If you are familiar with, or if you have been involved in wind tunnel testing or design of complex bridges, this concept is mainly in their laboratories is done day by day, day after day. But in the real, what we are trying to do is actually bringing this capability into the real life. So a little bit, first couple of slides are going to be about me kind of summarizing my own background information regarding Fred Hartman Bridge. So if I'm misrepresenting anything, please correct me at the end of the presentation. So this bridge is one of the two longest bridges in Texas, and then this one is the longer one. It's a twin-deck cable-stayed bridge with a main span of 1,250 feet. Each deck, this is a twin-deck diamond-shaped bridge. There are 992 cable stays arranged in inclined planes. Some of these cables are, according to the nomenclature, yard, which is kind of extending out of the deck a little bit, and then it's connecting Baytown with LaPorte. A little bit of history again. There has been, since the opening of this bridge from 1997 to 2005, there has been some monitoring work. There were several accelerometers installed on this bridge, and then there was a study out of this 8-year data collected in terms of the dynamic performance of the bridge, especially in the context of adding dampers on the cables and before and after. So what we're doing, following some cracks or some problems, high vibration problems on the cables, there was a need to look at the data and then do some kind of mitigation work by adding dampers on this bridge, and then to understand if the addition of dampers solved the problem, or like what's the current condition or baseline of the bridge. That was the idea. And there's another one, there's another study actually that took place in 2001. I think University of Texas was involved in this one. There was an acoustic emission system installed on this bridge. And kind of collectively looking at these two instrumentation and monitoring results, my outcomes, my takeaway from reviewing these reports were there was definitely a kind of aeroelastic instability on the bridge, which partially mitigated by the dampers. But the performance dampers was somewhat satisfactory, but somewhat unsatisfactory, which we will dive into in further slides. And then the acoustic emission system, there are some unconfirmed indications of wire breaks regarding the acoustic emission system. I believe those are still being reviewed. The goal of our project was, after all those years, looking at how the bridge was doing dynamically. So the idea was creating the new baseline for the bridge through operational model analysis, and then looking at how the deck and cables, or together as a system, how they are behaving. Sometimes you are seeing or we are collectively seeing presentations where we look at the structural components specifically, we test them. If we are doing the NDT study, we can easily understand like delaminations, discontinuities in those members. However, sometimes I believe when we do measurements, we forget how the system collectively behaves together. At the end of this presentation, you are going to see that we will talk about coupled deck plus cable behavior, coupled behavior, which kind of is going to be a good representation of what I just mentioned. The scope of this project was by using our wireless distributed vibration sensors, extracting the resonant frequencies of the structure, damping ratios of the structure, and the corresponding model shapes. Then we will look at the cable tension estimation, and we will kind of do a deep dive as to some details or pitfalls that we need to avoid when it comes to cable tension estimation. We will look at the comparison of as-built tension values with the measured values, and then finally, we will do some comments on the cable damping estimation. So just to clarify, for this bridge, we didn't have a chance to test. We only looked at selected cables, and then we didn't have a chance to look at, kind of disconnecting the dampers and do before and after damper kind of study. So we just tested them as the dampers were already connected. And then our results basically will indicate that. Now, a little bit theory behind operational model analysis. So before we do that, actually, maybe I should tell you what OMA is as a definition. And I'll try to do my best. So if there's like a bell here overhanging, and if I'm hitting that bell with an impact hammer, it's going to vibrate as a combination of easily visible dynamic motions. Right? It's not going to be visible to the eye. What you are going to see is like the sound, and then maybe a complicated vibration behavior. But there is a way to decompose that and then find those individual motions. And then actually, in your day-to-day in design work, when you click on a finite element computer model software and then do a model analysis, right? Especially if you are doing earthquake-resistant design, you should be familiar with that. That finite element software is doing is just the same. So what we are doing is taking that and then doing that same thing in an observable field environment. So our system in this case is the bridge. Our inputs are whether traffic or weather conditions or any external thing. If there's like a movable bridge, if there is some bascule bridge that has machinery inside, all those things are input to our system. And then what we measure through our sensors is the output. So what you are looking at is input system output kind of linear time invariant system, and you are trying to resolve how the system is looking like. This is a very well concept that's understood in electrical engineering and mechanical engineering, but this is a new concept for civil engineering. So what we are doing is basically understanding how the system is behaving. In terms of operational model analysis, we don't have a very easy way of measuring the inputs, so we are only looking at outputs. Output meaning the structural response to all those external activities. So what you're seeing on top middle section of this slide is a typical vibration signature out of one of the locations on the bridge. And then what we do is by combining all the measured spots on the bridge, identifying all the peak frequencies that is inherent to the structure. So this is the same analogy when you are playing, if you owned in the past, early 1990s, a nice tape recorder with like nice synthesizer with LED lights on it, and then when you're playing a music, it shows all those up and downs and everything. So this is the same idea basically, but in this case, bridge is moving, and then you are looking at those motions. And then individually, what we are doing is decomposing that complex behavior into understandable modes, which we'll talk about, and those are generally in the form of translation, bending, rocking, or torsion. In the case of wind monitoring or wind performance, torsion is being the most important case. Again, going back to the theory, design, again, day-to-day work, when you design a bridge through a finite element modeling software, you can either look at your system based on how you build your system. It could be a single degree of freedom system. In this case, on top left corner, you're looking at a continuous bridge with the pier and deck completely integrated, and then you are expecting only maybe a longitudinal motion. If you assume that your bridge is going to design that way, then you are looking at a single degree of freedom system. But of course, the case is never like that. You have a much complex behavior. That's why you are discretizing your finite element model, and then assuming that your mess on your model is concentrated on those sections, on connected sections, and then you are running your model. And then eventually, that is going to give you those individual modes. In this one, for instance, is generally the case for bridges. It's a half sine wave. So first mode is going like this, vertical half sine wave. And then the second motion you generally expect to be a full sine wave, like this, standing wave motion. And then as you go over the bigger modes, bigger frequencies, what you're going to see a combination of high frequency motions. Like it's going to be a, more tharas and valleys on your system, and also torsional modes. So what we do, now we are going into the observation phase, field testing phase. What we do is basically discretizing that multi-degree of freedom system into some equations that we can measure. I'm not going to bother you with too many mathematics here. What you need to know here is that in that third equation, that C is what we measure. And then through it's a matrix basically of measurements. Through the singular value decomposition of that signal, which is like if you have a linear equation of systems of equation, that's the way you basically solve this problem is through the single value decomposition. Actually, again, going back to the design stage, when you run a computer software with finite element modeling, it does the same thing. It creates a huge matrix of inputs that you define with your loads and everything, and then it kind of solves that matrix and then gives you the results. And eventually, all those peaks that you find is going to correspond to an individual motion. Now, okay, enough with the wizardry, how we can use this information. So one of the ideal ways of using this is creating more realistic finite element models. If you have this information, and I totally appreciate that for typical, simple bread and butter bridges, single span, short bridges, you may really not need to do any kind of this study. But for longer bridges, for bridges that you have high risk especially, it would be valuable to look at your finite element model and then see if the response of your model is actually aligning with what we are observing in the field. So whether you might choose to do a manual calibration or like an automatic calibration, there are some methods to do that as well. Basically, coming up with a nice finite element model will drive accurate results for either static or dynamic interpretation of your loads. Right now, there's a lack of verification at the design stage. As I told you, more and more actually, we are seeing a lot of complex bridge designs going through wind tunnel studies. So the idea is basically when you create a model through wind tunnel testing, you try to understand if your model is giving the same results. For almost all the long span bridges around the world right now is going through these tests. And then people kind of get their models verified through that. Again, for finite element modeling, if you are doing dynamic analyses in your model, the way you look at your model mess, where they are concentrated, and then how each mode has more model mess participation can be done through model analysis. Also, I mean, we all know that during construction phase, because of some uncertainties or some things that go sideways, the original design may not really be satisfied. This is also a way of understanding where your problems occur, or by looking at the dynamic results, you can understand if the deviations from the design is really creating a problem for you, for your system over the long term. I mean, nowadays, bridges are built 50-year, 100-year design life, but because of those construction maybe failures, we are looking at 5-year, 10-year problems along the way. So by satisfying some sort of post-construction validation through this method can actually be very valuable. And also for, again, most of the bridges that is not existing right now, we can look at we can reveal the unknowns regarding your bridge. This can be in the form of, again, how the bridge is dynamically behaving, or simply if you have modular joints in your anchor joints, basically, you can look at if they are contracting or expanding as they are supposed to, or how your cables are behaving, or overall if the frequencies of your structure is shifting over time, which will indicate something regarding the stiffness of your structure is deviating. So how we can do this in the field easily? As Geocomp, we have a very efficient way of doing that. We have wireless, super sensitive vibration measurement nodes. So these nodes can be deployed into the bridge, whether it's long span or short span, with either like a few foot distance between them or long distances between them. It depends on how densely you want to cover your structure and how much time you want to spend in the field. By just dropping them and then taking 20-minute measurements, you will be able to see all these results easily. So going back to the field's operational model analysis of Fred Hartman Bridge, we used only 104 data points. All these green dots you are seeing here is actually covering from one joint on the first back span all the way to the other joint. We had only a limited number of nodes, in this case 19 or 20 nodes. So what we do is we drop them. There's no anchoring to the deck whatsoever. You just drop them in there, collect 20-minute measurements under normal ambient conditions, and then you take them and then move to the next stage, and then until you get to the other side of the bridge. Simultaneously, as you are doing the study, you build your geometry and then upload your data to cloud, where we run our sophisticated algorithms to break down our mode shapes, basically. So this is the result from Fred Hartman Bridge. As you can see, almost all the critical frequencies are within 0 to 1 hertz range. So the first one is what you're seeing is that sinusoidal shape at 0.29 hertz, vertical mode. And then that vertical line actually you are seeing is one of the towers, because we were able to instrument one of them as well. The second vertical mode is the kind of like a full sine shape at 0.38 hertz. And then as we go further in the modes, we are going to see more and more harmonics of those same modes. And then the first torsional mode, which is really critical, is at 0.69 hertz. And if you want to take this further, you are going to see much more complicated shapes. Now, these high mode shapes actually generally more related with individual components of the bridge, not overall behavior, but for instance, at 10 hertz, 20 hertz, 30 hertz, if you have like a component, mechanical component on your structure, you are going to see them independently behaving or moving decoupled from your structure. So those are the things that we are looking at on the higher frequency phase. On the lower frequency phase, we are more looking at overall shape, global shape, which can create high forces when it comes to earthquake and wind. Again, we only concentrated on this green portion you are seeing. All those peaks are corresponding to the modes that we extracted. And then all the red light, the red part is the part that we really didn't touch, and more related to local behavior. When it comes to cable estimation, what we looked at was tension estimation of those cables and damping performance, and then a measure that we we are using, but I'm not sure how common that is, which is called Scruton number. It's a PTI recommendation, and it's according to PTI guidelines, it shows how susceptible your bridge to the wind loads, which we looked at as well. Now, cable tout estimation is the method that we followed here. You've seen other presentations as well yesterday and today. We are looking at extracting as many mode shapes as we can to understand if we can really apply tout cable method. Because one thing that's kind of being overlooked sometimes is that tout cable estimation only looks or assumes that the cable is working linearly. But most of the time, when you especially extract really high modes, in this case, we are able to extract 20, 30 modes, you are seeing that the behavior is really deviating from that linear range to the nonlinear range. It was quite, in the case of Fred Hartman, most of the cables were following the linear phase, but we already looked at like 3 or 4 other bridges where we saw nonlinear behavior, especially when you have larger diameters, varying diameters, and then heavy cables, then the stiffness of the cable becomes quite important, and then you need to consider those differences as well, which we are able to estimate. So these are the 6 cables we looked at. As what you can see in this graph is the Blue ones are actually the as design, the red ones as built records, and then the green ones are estimation. For cables 20, 22, and 24, we had some differences. Of course, in order to estimate and in order to come up with a conclusive result, whether or not the cable estimation results are, cable is kind of overtensioned or low, not overtensioned, you need to look at more cables and then basically symmetrically evaluate the structure. In this case, by just looking at these 3 cables, our initial assumption was maybe there might be a possibility that one of the cables which lost tension could be carried, or the loads of that cable could be carried over by other 2 cables. But it's yet to be verified, of course, with more cables. So I'm going to skip this part and directly go into this. The one you are seeing on the left is from the 2005 report, where they are looking at the current cable damping that's the dampers are providing right now. And according to that, we are able to damp heavily the first mode, but the rest of the modes are kind of partially ignored. So what it means is that if you have a wind actually blowing and then exciting your second, third, fourth, fifth mode, then your dampers are not going to be as efficient. And then the other thing that you need to be very, very careful about this is that when we look at the damping performance, we should extract the damping ratio information out of the cable. If we are only looking at how the vibration signal as we if we are doing a cable plugging test, I mean, there's a method that you hit the cable or to pull the cable, things like that. It's very easy to basically misrepresent, or not misrepresent, but misread the results. So you have to be very careful and do the right damping ratio estimation to understand the real damping behavior. Here in this one, you are seeing, the first mode damped heavily by the dampers, first mode only, but the rest of the modes are kind of somewhat effective. And then the funny thing is, on AS24X, you are seeing like a really high damping ratio extracted. And if you look at the main frequency of the deck, this is overlapping with the exact frequency of the deck at that time, at that mode. So that means some of the cable and then deck coupling might be affecting the damping of the cable as well. Another result you're seeing here is that from the first and fourth cable, from the first and fourth mode for all 5 cables is that on the AS22 for the first mode, you are seeing a really high damping, and then on the fourth one, you are seeing another type of high damping. Scruton number from PTI guideline. We looked at the current case regarding the first mode, and half of the cables were effective. And then we also looked at the worst case, where we looked at the least amount of damping ratio, and then found out that the scruton numbers were a little low. And I'm going to skip this part just to be efficient for time. And then another interesting thing we saw was that, again, this is based on the limited results, where the cable portion of the bridge where we estimated the cable tension and saw some higher, lower tension of the cable, we saw some asymmetry on the deck behavior as well on the first mode. So we are looking into what could be the meaning of this. We are trying to interpret the results with Texas DOT with some more information. Again, but takeaway is that we have to be really careful about the cable force estimation. We should be looking at how we are evaluating the damping information. Also, we also have to look at how the structure is behaving overall as a global system, not only concentrating on the local elements. With that, I'm just going to wrap it up. I hope I was okay.
Right on time.
And I would like to especially thank Texas DOT. I mean, it's one of these DOTs who are proactively, relentlessly doing a lot of preservation work. And then, the first presentations always is just amazing to me because it shows me how much people are relentlessly working with such limited resources. So thank you for that.
We have time for a question or two. Does anybody have a question? All right, excellent. Thank you very much. Great job.
The preceding was produced by the National Center for Pavement Preservation. More information can be found on the web at pavementpreservation.org. Additional support provided by Michigan State University.